Hello, everyone. I hope everyone is doing well and hope you have enjoyed this semester so far. For this upcoming months, we're going to working on a new topic, which is longitudinal data analysis. In today's class, we are focusing on 4 areas. We'll start with some basics. Then we're talking about exploratory data analysis, EDA, and touch briefly about different roles of covariates. I thought this might be something will be interesting and useful when you are doing analysis, thinking about covariates can have many different roles. And finally, we will working on some pre and post analysis, which is for a simple situation of longitudinal data. For those who wants to explore further, here I provided some references, and these references are mainly targeting for graduate students with more statistical focus, but there are many quite very useful examples presented throughout this books. So if you are interested in, you can looking at some examples there and looking at how they interpret the results, and so many mathematical derivation and theory. You might, if you want to go further, you can just skip that. Okay, so what is longitudinal data? Longitudinal data refers to the situation where multiple measurements are collected on the same individuals repeatedly over time. So the data consists of repeated measures of the outcomes and a set of covariates including time. For example, in a study of cognitive function, subjects are followed at multiple follow-up visits for repeated measures of a specific cognitive function outcome. Now, in contrast, cross-sectional data refers to the situation where measures are collected on each individual at a single time point. So while we collect longitudinal data, there are quite a few benefits, but mainly are for characterizing changes in outcomes over time and identify factors for the changes. So so just keep in mind the longitudinal data have to have at least 2 time points so that you can study the changes. And the cross-sectional data, only 1 time, each individual contribute 1 observation at a single time point. Just give you another example. This is a weight loss study. For example, if you want to examine the effectiveness of a single weight loss intervention, so we will recruit people and apply the intervention. We follow them for weight changes. So here, since we are interested in weight changes, so outcome will be weight measured at follow-up visits. Now, primary predictors are the group assignment, intervention versus standard of care, and the time. Why we need time? Time is because we examine changes, right? Changes from baseline or rates of change. Covariates can be many, could be demographics and the clinical factor, body mass index. And collecting this data allows us for characterizing changes in weight over time and examining the factors that influence the weight changes. Now, in this lecture and throughout the rest of the lectures, I'm going to use this example. And this is to illustrate the methods and the results, and also homework have that part. So let's consider a surgically interventional study to evaluate whether a new surgical method improves health and clinical outcomes in patients with a neurological disorder disease. The subjects were randomized to receive one of the two surgical treatment methods. Let's just call new method versus conventional method. And the subjects were followed over time, and the yearly measurements were collected at year 1, year 2, year 3 following the surgery. And the outcome interest is quality of life measure. Predictors include the group assignment and the times at which the data were collected. Now, statistical field we call predictors. And in epidemiology field, the primary predictor sometimes called exposure. So exposure are the primary predictor that you are interested in. Covariates. So here I'm distinguishing predictors and covariates. And in some literature or article you are reading, then they may just predictors, explanatory variables, covariates, exposure, they all may use exchangeable, but just understand here, we have a primary predictors are the group assignment, for example, treatment group and the times. And the covariates here, we refer to the background information, background variables, demographic information, clinical factors. And later on, I will tell you that these covariates can play many different roles. And this study included 115 subjects, with 55 with the new surgical method and 60 underwent the conventional method. So this is the example, the working example. I'm using this throughout the lecture and also the next several lectures. So this is the data look like. For example, I have subject ID 1 to 115 and surgical method indicating which surgical type the patient received. And the qualitative measure have yearly measure year 1, year 2, year 3 after the surgery. And there's also baseline measure before the surgery. The overall research question is something like, is the new surgical method better than the conventional method in terms of improve the quality of life? So what does this question mean? This is an overall clinical question. And translate this question to statistical question is something like, does the new method result in a greater increase in quality of life compared to the conventional method? Are the patterns of change different by groups, if not linear, right? Here I just introduce briefly about the notation, and later on I will have a more notation, but here this just the notation is we for longitudinal data we need two indices, I and J. So let's say Yij denotes the response of interest for the ith subject measured at the time Tij. So I have n subjects, then for each subject have repeated measurements. Now, using n sub I denote measurements, the number of measurements may not be the same across subjects. And then for each subject I, so the data is vector. This vector contains all the measurements for the subject I. So for example, this is subject I, so the first time, second time, third time, and so we're using Y sub 11, Y sub 12 denote the subject I, the serial repeated measurements over time. Now in this case, I show you the balance case, but this is not always not necessary. Okay, let's move on. Exploratory data analysis we call the EDA. So EDA, we perform EDA prior to formal statistical modeling. Why we want this? What is the purpose of doing this? So the purpose of doing is to inspect basic features of the data. For example, what is mean response over time? So how mean response change over time? Is it increase or decrease, or is increase first, then decline, following by decline? And what is the data variability over time? And the correlation, this is the difference between longitudinal data compared to cross-sectional data, because observations collected from the same individuals are correlated. So we want to expect what the correlation look like and how it varies over time. Of course, we are interested in the effects of covariates on these quantities. So the purpose of doing EDA is we want to make sure that statistical models for subsequent inference will capture these data features, and all the models we propose will be consistent with the data feature reviewed, right? If the data increase, response curve increase, or nonlinear, we need to use the model that be able to capture this nonlinear pattern. Now let me go through all this one by one. Now start with mean response over time. So go back to the example. We have 4 time points baseline, year 1, year 2, year 3. Quality of life is the outcome of interest. Intuitively, we could say we just plot all the points at baseline, year 1, year 2, year 3. And we calculate this sample mean. And this sample mean shows that group 1, both group 1 and group 2, quality of life improve over time. Also, this improvement exhibits a linear trend. Now, there's no substantial evidence that this is nonlinear. It's pretty much follow a linear trend. We can also tell that group 2 has a better improvement compared to group 1. And also we can tell that the data variability is increased over time. Now this is always, most of the time is the case, because at the baseline, because you do, for example, you do randomized study, the baseline usually people are similar, or not similar, you still have a variability. But over time, because individuals respond to the treatment differently, so you usually will see the variability increase. But again, this is not always the case. And go back to the data look like this. So we can calculate for each time point the sample mean. So it is the Y bar, sample mean. Then you can inspect this mean response over time. And this mean response over time is often also called population average response, population average. Because we use sample mean to estimate population average. So this is easy, right? We just calculate sample means at the different time points. We connect the sample points, sample means, we compare curves by the group. And also we will use this population average response, this terminology later. But here, just keep in mind that this mean response is often also referred to as the population average response. Here are some more examples about the mean response over time. There are many, but just to give you a list of like for some common examples. Let's go through this one by one. Figure A is from this mean response curve, you can tell that the quality of life means the two groups have the same mean response at baseline. But over time, placebo does not change over time, but those receive treatment improve over time. And figure B tells that both groups improve quality of life, have quality of life improved over time, but treatment group improve much better than placebo. this is a time, right? Time 1 and 2. So you think about time 1 is baseline, time 2 is follow-up. And the figure C tells you that is there treatment effect? The two groups have exactly similar change, exactly same change over time, but they differ only at baseline. So in this case, there's no treatment effect because both placebo and the treatment group exhibit the same changes over time. There's no treatment group. The two groups differ is due to the difference at baseline. And figure D, it shows that both groups did not change over time. No change over time, but differ at baseline. And so this is, now you're doing this EDA, and that will help you to set up the model. And well, this figure, you see that, right? This is the population average mean response over time. This figure does not tell you individual trajectory. And so if we were interested about individual trajectory, then we can plot, alternative plot is called the profile plot. This is just a connect observation for each individual, each subject, and you plot this subject 1, 2, 3, 4, for example. Then you just connect their observational data. And this allows you to discover variation in trajectories across subjects. And from this, I figure you can tell that what are the variation. Well, first of all, starting point differ. Translated to statistical language, this is intercept. Each individual has their own intercept. There is variation across subjects in terms of the starting point, baseline value, intercept differ. And in terms of changing over time, if you look at this subject 1 and 2, yes, they increase over time, quality of life changing over time. But this changing are similar for subject 1 and subject 2. What does that mean? This means is a slope. Slope over time, slope is interpreted as a rate of change, is similar for subject 1 and subject 2. And if you look at subject 3 and 4, they show different pattern, right? They increase from baseline to year 1, then level, they not have is level parallel, then after year 2 and increase again. Now, if you imagine that, say, if I have study population, I have half of them in treatment group who shows this relationship, and for those who receive who in the another treatment group and show this relationship, then obviously then the group 1, the group 1 and the group 2 differ in terms of how this change over time, and the variation most come from the intercept. Once you're controlling for intercept, in terms of rate of change, there's not much variation across subjects. So profile plot and the mean response plot is giving you complementary different perspectives of the data. The mean response show you what population average change over time. It does not tell you how these individual change. And the profile plot and show you how individual trajectory change. And in next time, when we talk about the linear mixed effects model, we will use this concept that this is intercept vary across subjects. And we will also model how the slope vary across subjects. So keep in mind, so this is this is another way of looking at the longitudinal data is looking at the discover variation in trajectories across subjects. And this plot is useful if you are interested in about doing prediction of individual future outcome. So this will be very useful. It's a useful plot to look at. And what is about correlation? Why we want to inspect the correlation? Because inspecting correlation can help determine the type of model you're going to use. And again, we back to the data look like, and this subject I, so subject I repeated the measure like this, and the subject 2, then by time, and the time 1, time 2, time 3. And intuitively, you will see, intuitively, you expect that observations in time 1 is more strongly correlated with observation in time 2 than observation time 1 versus time 3. And so the correlation is the longitudinal data different from cross-sectional data is longitudinal data have correlation. Why is it because the observations are no longer independent. Observation coming from the measure from the same subjects tend to be correlated. Example is blood pressure. People with high blood pressure, their series measure from the same individual always around 150. So for example, 150 systolic blood pressure, and those around 110 always is fluctuate around 110. So individual, there is a difference between individuals. That's the correlation, because the measurements coming from the same individual tend to be more similar than in measurements coming from different individuals. Another way of looking at the correlation is that correlation as time. So for example, this just mentioned that, for example, if you plot the scatter plot of measurements for time 1 and time 2, and compare time 1 and time 3, so you expect this is less correlated, weaker correlation, weaker compared to time 1 and time 2. So as the time and the separation of the time intervals increase, the correlation among the between the measurements decrease. And this needs to be taken into account in the model we're going to talk about next time. And because correlation will affect the efficiency, the standard error of the estimates. And for the same data, back to the same data, we can calculate, in addition to make this figure, you can calculate the sample correlation. You just correlate this time 1 and time 2. Then you can find this, you can make this sample correlation matrix. And basically you can, for each time point baseline, you correlate the baseline measurements at baseline to the measurements at year 1. So you can do pairwise correlation. And this table just tells you that the estimated correlation, sample correlation between measurements at year 1 and year 2 is 0.65, which is stronger than the correlation between year 1 and year 2. So this is the sample correlation. And we will use this correlation for next time when we fit a marginal model and linear mixed effects model. But here, just heads on is up front and get familiar with the data are correlated. Okay, just to summarize, in terms of covariates, as I said, is you can plot this by age, by gender. You can plot this also by age, gender. And so this EDA you can do you can extend right to many subgroup analysis to understand whether this pattern differ by covariates. So summary, EDA help us figure out the initial model. So recall our objective of longitudinal study are to characterize changes in outcomes over time and determine whether the changes are related to covariates. So the changes include mean response change, population average change, also include, for example, individual trajectory changes, and variability data, how variability data change over time, and how these these characteristics related to by age, gender, race. So the EDA help us figure out the initial model. Okay, so now let's understand some different roles of covariates. I thought this might be interesting for those who are not familiar with this. I'm sure some of you are already familiar with this, and but just let we get familiar with the terminology. Now, first of all, you must have heard that the confounding factor. So what is a confounding factor? A factor is called a confounding factor if it is associated with both outcome and exposure. So recall, the exposure mean is the primary predictor. And so here our primary predictor is the treatment group. It is not in the causal pathway between exposure and outcome. So let's look at this simple diagram. See, we are interested in treatment effect on quality of life. So basically, we are interested in the relationship of surgical treatment method and quality of life. Now, if it happens that treatment group, those who receive new treatment group are younger, contains more younger people compared to the conventional group. So the age is younger in the new treatment surgery compared to conventional surgery. And it's clear that older people, younger people have a better quality of life. So think about the quality of life is the instrument have many different subscale to measure, and you find the quality of life as a composite score. Quality of life measure, for example, have a many domain measure pain, sleep, what's the others? How you feel, how you happy about your family. These are the kind of measure of quality of life. And so quality of life usually is a continuous scale. So usually you intuitively younger people have a better quality of life, have a larger, the greater value of quality of life means better quality of life. So in this scenario, age related to surgical group, because younger age, surgical group, a new group, is younger compared to conventional group. Age related to surgery group, age related to quality of life. So meet this condition. A factor is called a confounding factor if it is associated with both outcome and exposure. This is exposure. And it is not in the causal pathway because age cannot be modified, cannot be changed due to this exposure, cannot be the consequence of exposure and outcome. So age is confounded. So age confounds the relationship of treatment and quality of life. What is consequence of confounding? It marks the true effect of the treatment, right? Because when you ignoring the age group and you find that the new treatment group resulted, you might say, the new treatment group resulted in the better quality of life. Because quality of life is better in the new treatment group because new treatment is younger, right? But in fact, this is the relationship is due to the age, can be attributable to the age. The relationship, the better quality of life observed among those who receive new treatment is largely due to their younger age. So this is the concept with this age as confounder. Age confounds the relationship between the true effect of the treatment. So our statistical model needs to take into account adjusting for the age confounder. So one way of doing is you including the age in the model. So this is one type of, we want to say, confounding factor. Usually age demographic information, it is a confounding factor. And the moderator. What is moderator? Moderator, sometimes also called effect modifier. Effect modifier. Moderator is a third variable that affects the direction, and or strength of the relation between an independent variable and outcome. Sorry, let's move on. Let's look at this diagram again. So I have a relationship here, and think about age and sex is the third variable that affects the direction and the strength of the relationship between this independent variable exposure and outcome. And what does that mean? This means, for example, if the treatment effect, okay, surgical effect on better quality of life is stronger in older age compared to younger age. So the effect of the new treatment that improves the quality of life is stronger. There is a larger effect of treatment. There is a larger effect of the new treatment, new surgery on quality of life in older people compared to younger. So this is effect, the strength, the relationship. Now sometimes it may be opposite relationship. There maybe you see the positive relationship. This may not be this case. For some other studies, you might say, okay, positive relationship between the surgery, particular treatment for improved quality of life only occurs maybe in older people, but not in younger people. Younger people may see the opposite relationship. Now, I'm just hypothetically for, if you see the effect of the direction, that's also moderate effect modifier. Which is in summary, just we say that the relationship of the treatment and quality of life differs depending on the level of a third variable. Here is, for example, age, older versus younger, and the gender. Now, in this case, this third variable called moderator, effect modifier. Statistically, and how we do that, we can make this, we can testing for interaction. Interaction and can tell if the variables acts as a moderator. And but in many analyses, testing for interaction does not have sufficient statistical power. So you have to you look at this as like from using your domain knowledge to guide you whether this variable might be served as a moderator. And now if you feel this is a moderator, what do? You do subgroup analysis. So in this case, you do your analysis of looking at the effect of surgery on quality of life separately to subgroup analysis stratified by age, stratified by gender. And another type of role is called a mediator. So a variable is said to be a mediator if it accounts for, to some extent, the relation between the predictor and the outcome. And so mediator Z explains the relationship of X and Y. So it explains the relationship. Okay. Let's go back to this example again. So here, there is a relationship between surgery and the quality of life. We observe that a better quality of life among those who receive new surgery. There is a relationship between surgery group and adverse event. For example, if surgery, new treatment, new surgery reduce the occurrence of adverse events. For example, epilepsy, seizure. And of course, there is a relationship of adverse events and the quality of life. Like better quality, people with better quality of life does not have many adverse events. Effects A, B, C all exist. All exist. Now, the effect of the treatment, see, the effect of treatment on better quality of life was found. We found a relationship. But the effect was reduced when the third variable, adverse event, was added to the model. So these are the situations. Adverse event is a mediator. Adverse event actually is in the causal pathway. Surgical group influence adverse event. So actually this is the error is wrong. This should be the other way. So think about the other way. So surgery, this is wrong. Okay, surgery group affect adverse event. So this should be changed this error to the other way. Surgery group affect causal. The adverse event is the pathway from surgical group to outcome. So this is the mediator. How do mediate means that adverse event explain the relationship between surgical group and quality of life. In other words, that better quality of life observed among those who receive new treatment, new surgery, is because of they have fewer adverse events as a result of the new surgery. So here adverse event is a mediate the relationship of surgery method and quality of life. Okay, so in summary, mainly you can classify covariates into confounder, moderator, mediator. Mediator, it occurs in sequence. It occurs after exposure. So exposure first, followed by mediator and outcome. So mediator is in the causal pathway from exposure and outcome. So there is directionality, right? And causality also. So mediator, like adverse event, is a result of surgery. So mediator has a time sequence. So in the longitudinal data setting, mediator is usually time dependent. Right? So you measure, for example, here the example is surgery and quality of life. So everyone receives surgery. Then over time, year 1, year 2, year 3, maybe there are adverse events changing. The likelihood of developing adverse event is lower among those who receive new treatment compared to those who receive conventional surgery. Then which ultimately leading to the better improvement, better quality of life among those who receive new treatment. So mediator is the causal pathway, and mediator usually is a time-dependent variable. And confounder, different from mediator, no causality, is no time sequence. Usually variables cannot be modified. Most usually demographic information and the baseline medical condition. And we see possible baseline medical condition, but the age, gender, race, and the moderator is affected the direction and the strength of the relation. This also different from mediator. Also no causality, and usually variables cannot be modified. And this all depends on the analysis and objective of the research question. So in certain type of analysis or research question, the variable might be the confounder, but in some other analysis may be moderator. Like for here example, age might be confounder as well as moderator. So in this case, some analysis you want to controlling for age, but you might also want to do subgroup analysis by age. In this case, doing subgroup group analysis by age, you want to examine whether age modify the relationship of X and Y. Right? So here this example, if the effect of treatment is stronger, the effect of treatment on quality of life is stronger in older people compared to younger. When in subgroup analysis, then you can say, okay, age is a moderator. Now, if you do the subgroup analysis, you found that the relationship, the effect of treatment on quality of life is similar in older compared to younger, then age is not modified, does not act as a moderator. Then you can just combine the younger and older as an overall analysis. So this is so some variable play a confounding role, and in particular analysis, they may play moderator in another analysis. Same as mediate also. Mediate also possible. Like if the adverse event measured at baseline, and they may serve as confounder also, because you want to looking at the effect of surgery on quality of life, controlling for baseline medical condition, baseline clinical condition. And in that case, an adverse event at baseline is confounder. Okay, now we are, so what time now? Okay, so we have time. So we are ready for doing a pre and a post analysis. And the pre-post analysis is for a spatial situation where a single baseline and a single follow-up measurements are collected from the same subject. And the purpose is to examine pre and post changes and examine influence of the predictors on pre and post changes. Pre and post changes. So just now, pre-post analysis is not really longitudinal analysis. The method I'm just show you later is actually cross-sectional analysis approaches, but this is so it's not new. It's not new. You can use all you learned so far to do pre and post analysis, but pre-post analysis is so. But it is for longitudinal data because there is a 2 time points data on 2 time points involved. One is baseline, one is a follow-up measure. So I put this here, but I'm not quite sure if you already learned this from your previous other analysis. But the method I'm showing now is for cross-sectional analysis approaches. You will see this in a minute. Just for the purpose of post analysis, I'm here introduce notation. Y I0 I null denotes the response measure at the baseline. So is 0 represents baseline for subject I, and Y sub I1 denotes the response measure at follow-up time for subject I. And see each subject has a pair of measurements, one at baseline, one at follow-up. So 0 denote baseline, 1 denote follow-up. Then let's just say, okay, I have just 2 groups. So I introduce X sub I is a binary indicating variable, 0 indicating control group, 1 indicating treatment group. So just for simplicity, I'm consider 2 groups, but you could extend this to 2, 3, 4, 5 groups. There are basically 3 possible approaches, analysis approach. One is you just use the follow-up value. So you just using the regular regression model, where follow-up value included as the response variable, and the covariate just the group indicator. So for each individual, you ignore baseline value. So just the model includes follow-up value as the response variable, treatment indicator as the covariate, as the exposure. With this model, you see that the beta sub-zero represents the mean response at the follow-up for the control group. So right, this is because I'm coding x 0 for control group. So when x equals 0, then this is gone. This is error term. Then I get the expected value for response at a follow-up. And the beta sub-zero plus beta 1 is the mean response for the treatment group, because I'm coding x equal 1 for treatment group, then beta now plus beta 1 is the response for the treatment group. Then beta 1 is represents the difference in the mean response at follow-up for the treatment group as compared to the control group. So this is the estimated treatment effect using this model. Clearly, right, this analysis is valid if the baseline values are balanced, are comparable in two groups. For example, where assignment to the treatment is randomized. If the baseline values are incomparable or substantial difference, then this method will not be valid, will not give you valid estimate of the treatment effect. Another approach is looking at the change. So you just replace this response variable by the change from the baseline. For each subject, you calculate the change from baseline, then use this as the response variable linked to the treatment indicator. So the beta 1 represents the difference in the mean change for the treatment group as compared to the control group. Now, so using this model, beta 1 is the estimated treatment effect. This model sometimes called the unconditional change score, unconditional change analysis. And appropriate in either observational studies or randomized studies, can be used for any types of these studies. And so what does this mean? This means just two groups, I just find the changes. I just find the changes, then examine whether these changes, mean changes, are same or different in these two groups. So this is unconditional changes. Another approach is called ANCOVA. So this is similar as is sometimes called analysis of covariance. In the regression model setting, is you're using the follow-up as the response variable. Then this is still treatment indicator and the baseline value of the response variable included as a covariate. So this model, how this model taking care of the baseline is by including baseline as a covariate, and then you run the regression model. So in this model, the interpretation of beta 1 now is interpreted as the difference in the mean follow-up response comparing subjects of the treatment group to subjects of the control group, given that they had the same baseline response values. What does that mean? This means I got the estimated treatment effect after adjusting for baseline. So this model is called like a conditional model. So you conditional on subjects of the two groups who had the same baseline values then looking at their follow-up mean response. And this model is appropriate when treatment is randomly assigned. And there is a discussion about this model may not be good for observational study. And it is recommended for randomized study. However, this model have assumption. This model assumption is it actually assume beta 2, this is the relationship of baseline and follow-up, assumed to be similar in the two groups. What does that mean? Mean is there are parallel regression lines in the treatment group and the control group. So the relationship of baseline and the follow-up does not depend on the treatment group. That's the number one assumption. Then another assumption is the population distribution of the baseline responses are equal. What this means is that it requires this baseline value have the similar distribution. And there are some other assumptions as usual. For example, you want a constant homogeneous variance across the two groups. And this model, well, this model, you might ask why you want this model, why want this assumption, number one, number two, right? This model gives a more precise estimate of beta 1, give a more precise estimate of the treatment effect. Precise meaning is give a smaller standard error. So that's the benefit, again, you will get. If this assumption met, you're using ANCOVA analysis to estimate the treatment effect. But if this assumption not met, so you want to go back to the change analysis. Now, you can see that you compare these three models. This I said that this is cross-sectional approach. There's no repeated measure for each data point, right? This is the I data point. So each subject contribute one observation. You're using the follow-up in this model. Then here you find the changes. Then the next model, you're using the follow-up as response. Then you put the baseline as a covariate. So this actually is cross-sectional analysis. And the difference across these three models is what are the difference between these three models? So the three models differ in the way of treating the baseline. Follow-up, this model actually is totally ignore the baseline. Ignore the baseline. And this model, by taking into account the baseline through using change analysis. And let's see. And this model, ANCOVA model, taking care of baseline values by including baseline as covariate. So these are the different approaches to taking into account the base influence of the baseline. And we will see this more later, but these three models all give beta 1, give the estimated treatment effect. But these are the interpretation of this beta 1 differ under different models. Basically, is change analysis give unconditional change, just compare the changes. And this is actually is conditional. We conditional on the people with the same baseline value, then looking at the follow-up difference. And you can also do, here is the extension. Extension is you can add more covariates to the model. Okay, so these are the pre-post analysis, and still I have so many clinical studies. All these approaches are still very, and this is not very common, and the change analysis are very common to use. And you you can also think about if you have more than 2 follow-up measurements, and you can also do simple analysis, for example, by aggregating, say, for example, you have year 1, year 2, year 3 data. Then you can do year 1, year 2, year 3, year 4 data aggregate to be the average that compared to the baseline. Then you can, so if you, in the situation when you have more than 1 follow-up measurement, you can aggregate all these follow-up measurements into 1 follow-up value. For example, 1, 2, 3, 4, year 1, year 2, year 3, year 4, you can calculate the average, then compare to baseline using this pre and post analysis. And so this pre and post analysis are quite common, and if you, in some situations, are still very useful common approaches. And of course, this a general longitudinal data setting is much more complex than only pre and post. In the situation where there is more than 1 follow-up measurement, and also, and here I show you the repeated measure. The example I show you, repeated measures have the same times, measure on the same time. But in some other study, repeated measure may not be recorded at the same times among subjects, and also may be recorded at irregular intervals. For example, measure every month for the first 3 months of follow-up, and then every 6 months interval for the next 2 years, and every year for the next 5 years. And we need spatial methods that can analyze such data, and we're going to cover this in the next 3 classes. And just wrap up today's class. So we talk about the longitudinal data basics, and so it has to be involved at least 2 time points. So my question also to you is, say, for example, if I have a situation in the study that I have repeated measure for covariates and also for time, but my outcome measure only measure at 1 time point. Is this longitudinal study? I have a question to you. And also is we just to summarize, the longitudinal data has features. Important feature is the time scale, time. You have to have a time. Time is the important scale variable you want to look at. Using time, you can estimate the rate of change, which is a slope. You can estimate not linear, or maybe just the change from baseline at each follow-up time point. And EDA is allow you to explore like mean response over time, variability over time, correlation over time, and how this is related to covariates. And EDA, looking at EDA is important, and this is recommended done before formal modeling, because EDA can inform the kind of model you should start with. And we talk about the different roles of covariates. In particular, we focus on confounder, mediator, and moderator. This is in cross-sectional study. You kind of, it's hard in cross-sectional study. The role of this variable are hard to be differentiated. But in longitudinal study, you actually be able to do better job to differentiate the roles of these different roles. Like for example, mediator, of course. In cross-sectional study, you cannot identify mediator. But in the longitudinal study, you'll be able to identify mediator, because mediator always happen after exposure. It's in the causal pathway between the initial group assignment initial to the ultimate outcome. But in cross-sectional study, you never can tell this is mediator. You can always never can provide evidence this is the true mediator. And also now finally, we're talking about the pre and post analysis. You can use all you have learned so far to analyze and pre and post the data. So I have some data set and also have a SAS code for you to we can do together, or I don't know how, but I will post this on Wednesday about the data, so you can start using this SAS code to look at this, including some EDA and also pre-post analysis.